Hello, good afternoon, everyone. My name is Rocío García Alonso from Sustainable Innovations. I'm also the Communications Manager for the Perform project, and I'm very happy to be here. It's a bittersweet moment from all of us because, well, the project is ending, but we have this amazing venue thanks to our member Rosalba, and we're here to, well, the members are here to present the final milestones from this event, and I'll be very quick. To the persons that are watching this event on the live stream, you can make all the questions via chat, and at the end of the event, I will respond it to you. And to the persons that are in here, after we finish, we will have an amazing aperitivo in that room. So hopefully you will enjoy it. The first part will be introduced by Erwin Giling. He's the project coordinator of the Perform project. And then, he will present the project overview and the main results. Then we will follow with Rosalba Passalacqua, if I'm saying your last name correctly. Then Just Helsen from Vito. Then Riccardo Zaffroni. And we will finish with Alexandru Morosanu. After that, I will present again 3 videos, the final video from the project, then a video we made last month in Delft about a workshop, and also the video that you may already watch about Vito's role in Perform. After that, we will make the questions and answers from the persons that are watching this on the live stream, and then we'll have the network cocktail. So thank you all for being here, and I will give the speaker the phone to Erwin, the floor to Erwin. Thank you so much.
All right, thank you very much for the introduction. Good afternoon. My name is Erwin Giling. I'm working at TNO in Delft, and I have the honor to be the coordinator of the EU Perform project. And today we have the final event, and I will present an overview of the whole project, what we've done until now, and after that we will have a bit more technical presentations. So let's see if this works. Yeah. So what is the Perform project? It is a Horizon 2020 project, also supported by the SPIRE program. It is in the topic of processing of material feedstock using non-conventional energy sources. It runs from January 2019 to December 2023, actually 5 years, which is quite unique because we had a project extension. Overall objectives there are to develop a modular electrochemical power platform. I will come to that, what it is. Demonstration showcasing 2 processes. And of course, a lot of dissemination and exploitation activities. And this is one of them today. So what is the motivation of the project? Well, I think it's pretty clear for everyone that we need to decarbonize our society, both energy and feedstocks. And this picture says it all. We will go from decarbonized energy, let me try this pointer, and circular feedstock, so carbon that's circular, combine it, and from that we can make sustainable materials with a very low or zero CO2 footprint. And that is, of course, following the global trends on the energy transition and reducing CO2 footprint in the chemical industry. It contributes perfectly to a number of EU policies. It started a long time ago already with the Green Deal. And then from the Green Deal, there were a lot of action plans and policies implemented. Even during our project in 2020, for example, we have the Circular Economy Action Plan, make sustainable products the norm in the EU, less waste, more value, and also the chemicals strategy, boost innovation for safe and sustainable chemicals. So that is all the motivation behind the project, and it's still the motivation. So Perform aims to have safer chemicals, increased energy efficiency, renewable energy, of course, and use renewable feedstock. So there's a lot of topics that we address actually in this project. What is the concept? The concept is that in the middle here you see a schematic of an electrolyzer and some processing units. Renewable feedstock goes in. In our case, it would be based on biomass. And renewable power goes in on the top, and then high-value chemicals come out of the process. We started this with a low TRL, and the idea was to scale this up to higher TRL 5, 6. On the right, you see the structure of the project. So we've been working on the basis, which is the feedstock, and then, feedstock. And then we worked also on the electrodes that you need in a reactor, design the whole system, build the whole system, and then do some exploitation and dissemination from all the results. The consortium consists of 11 partners from 7 countries. You see on the right of the activities the companies from Avancium, who's working on feedstock and electrode development. HYSYTECH, main builder of the equipment. And Alex will also present today about that. We have Radici, Perstorp and Overmond on the company side to work on exploitation, testing, application testing, and also on the business cases. And Ava Baigam in particular also working on the techno-economics. On the left side we have the research institutes, INSTM, who is host of this meeting today. Vito and TNO, development of the different research lines. Hohenheim, preliminary working on the LCAs and also on the TEA, and Sustainable Innovations, who is helping us with commercialization, exploitation, and also impact analysis. What are the key technology results? Well, to the right you see the schematic of what we're actually doing. We have feedstocks, we have an electrolyzer, electrons go in and out, and on the anode side on the left you see an oxidation process, on the right a reduction process, and every site has its own DSP to produce a separate material or a chemical feedstock. So the idea is we do it paired. We do something useful on both sides in an electrolyzer. For example, if you would do water splitting for making hydrogen, on the other side you would have oxygen, which is quite worthless. We don't do that. We also don't make hydrogen. We directly can use the protons, and we have 2 useful reactions in one reactor using the same energy source. So we sort of use every electron 2 times, so to say. So paired electrosynthesis, a very important one. Then process intensification. Of course, you want to have high selectivity. You want to have that your electrons go to the right product and not to a separate side product. High conversion, efficiency of the conversion. And because it's electrochemistry, you have very mild process conditions. You don't have high pressures with high pressure oxygen or hydrogen in a reactor. It's all atmospheric conditions, which is very advantageous. We use flow chemistry for efficiency, not a batch chemistry. And other key technology results that we aim for are new electrochemical electrodes and reactors, just to achieve the goals that we mentioned in 2. We integrate everything in one process, and of course, very important, the PowerPlatform demonstration. So these are the key technology results of the project. So we built the PowerPlatform actually, and we used it for, the aim was to use it for 2 showcases. One line was the responsibility of TNO, where we did furfural to maleic acid conversion combined with levulinic acid to valeric acid. The other one was led by Vito, and that is actually a tandem reaction. So first we oxidize glucose to glucaric, and Joost will tell more about that later on. And then the aim was to go to adipic acid. And the latter one, unfortunately, didn't really work out as we planned. I'll come back to that later. So this describes, on one hand, the timeline of the project from 2019 to 2023, and also the scale-up that we did, from the analysis to the process integration design to the demonstration. And you see that actually we started with like small reactors, 10 centimeters square, 100 centimeters square surface area, and then we went to 1 square meter, which is 10,000 square centimeter. So you could say we are looking for a scale-up of a factor of 1,000 in one project. Well, that was quite challenging, We did it. Also, we're not there yet. This is the expected impact that was written down in the proposal. So the pilot, the energy efficiency, I won't go through this all, but you can also read it back on the internet later on. This presentation will be available after the event. I'll skip to it with respect to time because I want to go a little bit in specific results. So the feedstocks, we worked on this with development of the pretreatment and analytical methods. And of course, it's very important to mention that we also start from non-food biomass, for example, agricultural residues and forestry residues. And we get the glucose out of this, so this is for the second line of the development that we did. Catalyst and electrode development, Rosalba will tell a bit more about that in a later presentation. There were some objectives to reach: selectivity, efficiency, and productivity, and also stable electrode materials. That's always important. You want to run for many hours before you have to exchange your electrodes. So we proven that. We did make these electrodes with high ferritic efficiencies. However, we did not manage to do electrolysis to adipic acid, from glucaric acid. It's too challenging, and we did not scale this up. So the demonstration we've done with the line 1 paired electrolysis. We did develop novel electrodes, and we also did the scale up to the 1,000 centimeters square, and now we have a reactor with 10 of these cells, so total 10,000 centimeters square pilot. This is how it looks like in practice. So you go from a very small scale 8 cells via 10 centimeters square, 100 centimeters square to 1,000 centimeters square cells, and then to 10,000 centimeters square surface area, which is the pilot that is now in Delft at the laboratories. And we're actually still working with that, and we're still getting the latest data out of it, even if we are already almost in the last month of the project. Process development, very important. You have to get the products out of the electrolytes. So we worked on that, and we developed a complete integrated process. And it looks a bit like this. So we go from, we had to make several units to process the different electrolytes and get the products out. In particular, I want to emphasize a bit here, we have an electrodialysis unit, we have a concentration unit, a crystallizer filtration unit, we have a liquid extraction unit, we have to do distillation to come to the target product, and in this case, what you see here is maleic acid crystals. So I must say that was also a bit more scope than we had foreseen when we started the project. So here you see what we can do. This is the showcase where we go from furfural to maleic acid, so that is the oxidation side of the reactor. And we did obtain that already in the 1,000 centimeter square reactor, and later Riccardo will tell a bit more how that works in the pilot. And from that we get the numbers also that are important from the techno-economics and for the business case analysis. So what is the efficiency, what is the purity, how much energy goes into the separation, how pure is it, can we get the salts out, because for electrolysis you need salts and we use sulfuric acid, and you have to get it out, you have to recycle it back. And that whole process has been designed on lab scale first. And here you see that these crystals are coming out and are rather pure. So with all these numbers from the pilot and also from the lab experiments, we have done process assessment, techno-economic analysis, and also the screening life cycle analysis, where we want to determine the CO2 footprint of the whole process. And there you use all the numbers, you use scenarios, you can use intermittent energy scenarios. Oh, wrong button. Like this. And you determine the system boundaries of your whole model, and then you can compute, for example, what 1 kilogram of product will cost you in the future based on a certain scenario. So that leads to a business case analysis. Is this viable? Is this a viable process? Many steps, many things to develop. The conclusion for now still is that for the valeric acid side, if you go for livolinic acid, that's not a good business case. So we have to come up with another reaction on the cathode side, because at the moment it's not very viable. For the maleic acid, it is possible to have a viable business case. Adipic acid we did not generate, so these are assumptions based on the targets that we wanted to reach. But in the end, it shows that there is a potential for a positive business case, but it still strongly depends on the future price of the feedstocks and on the energy, and that's something we cannot influence. And in the end, it's always very difficult to compete with fossil fuel-based processes that are already developed for like hundreds of years. So you have to compare these numbers with other sustainable processes, for example, the thermocatalytic conversion of biomass, and then it's not so bad. So as a summary, as project overview, I hope to leave a bit more minutes to the technical presentations. Electrochemical conversion and integrated DSP was demonstrated on the lab scale. We built a flexible pilot platform on TRL 56, and we did a demonstration. The reactor is flexible in the sense that you can change it, you can change the number of cells, you can even change the whole reactor. You see it over here in the lab on this side. In the center you see the reactor itself, but there is a whole balance of plant built around it. It's still available, it's kit-based, it's modular. To the right side you see the electrodialysis unit. Alex will tell a bit more about this equipment and how we built that. The demonstration actually is still ongoing. I don't expect that we can finish all the campaigns that we planned this year. This means that we can also not finish everything in the project, but we're already talking about a continuation of this research after the project. Yeah, with that, I think I would like to conclude the overview and give the floor to the other technical presentations. I think this is the last slide, right? Yeah, so if you have any questions online, please put them in the chat or send them to me. My email address is over here. So thank you, and on behalf of the whole team, yeah, we want to thank you for your attention. So the next speaker will be Rosalba, and she will speak about the catalyst development and electrode development that we did in the project. So can we change the presentation, please? Not yet. Yeah, this works. Yeah.
Thank you. Good afternoon to all everyone. It's a pleasure to present this result concerning the PowerPlatform project. In particular, some results that are related to the development of the catalytic material used to prepare the lab scale electrode and used when after optimization for the preparation of the pilot unit. Just to recall the two performance showcases that Erwin have presented, and the technology, electrochemical technology approach that we have used in both cases for line 1 not work. For line 1 and also for line 2, our activities was devoted to the development of the electrocatalytic material. For the sake of for the brief time available, I show you only the first line concerning the oxidation of furfural to maleic acid. And here the motivation that give us the idea to investigate this reaction. Currently, the maleic acid is produced from essentially from materials that are produced that are obtained from fossil-based feedstock. And the interest in producing maleic acid is related essentially to the many applications of these building blocks that can be used for polymers and also biopolymers, for lubricant, additive, plasticizer, pharmaceutical, and also bio-based aromatics. So the idea to produce by electrochemistry the maleic acid through a route in which we start from a bio-based system and derived from the biomass, like furfural, was an interesting route because represent a green conversion route that can be used instead of the traditional current industrial production. So on this base, we have decided to investigate this reaction, and in particular the activity that we have obtained within the work package 2 of the PowerPlatform project was the development of the electrocatalytic system to obtain the reaction of oxidation of furfural to maleic acid. And we start from the catalyst selection, and after various steps, we finally obtain an electrode that was able to run the oxidation of furfural and a system that have the characteristics that are suitable for its use in the successive step of upscale. So the requirements are essentially related to the selectivity and the efficiency of the reaction, and the productivity of the system, and stability of the materials. And starting from the catalyst selection, this selection was made considering various type of catalytic material, for example, platinum, titanium dioxide, and so on. And to select the better component able to do the reaction, we use electrochemical measurement, in particular cyclic voltammetry, in order to identify the condition at which the oxidation of the furfular is obtained. We have identified the potential for this reaction in the different conditions, and we have also verified that the system was stable, the product of the reaction was stable in the condition of reaction from the cyclic voltammetry in present and in the absence of the product of the reaction. And after, another requirement of the catalyst for a possible development of the electrode was also his nature and his stability, the facility to have this material available, and also the economical consideration. A cheap material is better than a rare or noble or metal. So the selected material was lead dioxide, because other type of material that was in a first step considered interesting were not suitable for reason related to the low current density, so don't meet the requirement for the upscale. And the lead dioxide was obtained in a particular phase that was more active than the other one, the beta phase. And the material was obtained by electrode deposition, and here is reported electrochemical plating system and the condition for the electrode deposition, and relevant conditions that have been investigated during the preparation were plating current density, plating time, the composition of the plating time, and the temperature, because the beta phase require a higher temperature to be obtained. The material was deposited on a inert support that was pre-treated, and as support we initially used a titanium gauze, and here is how the electrode at the lab scale as appears after preparation. After the preparation, we ran the experiment, and so used the catalyst in the reaction condition in which furfural is oxidized. During this reaction, is not only present our target product, maleic acid, but we obtain also an intermediate 2,5-hydroxyfuranone. This intermediate can be easily converted to malic acid in a second step thanks to the recirculation of the electrolyte. And for this reason, we have conducted the experiment in a flow cell, like the one here reported from electrocell. Here the setup with the condition utilized for the electrolysis test, and how appears the electrode prepared, the first one, and we have prepared, and the second one that is quite different. I show you the next. What we do is the experiment for 3 hours, sampling every 30 minutes, and here are reported the result. The results are reported as combined Farad yield because two are the product, HFO, and the target molecule malic acid. And you can also see the profile of concentration and the Faraday yield of both malic acid and HFO, and the total combined Faradic efficiency in gray in this graph. But this material, this first material prepared, was not stable mechanically. In fact, you can see that is easily bendable, and so is not suitable for application in electrochemical, in industrial application. Another improvement that we have obtained was modifying the plating bath by adding PVA, a surfactant, in the electroplating solution. And what we have obtained was this type of material in which the morphology is better than the current electrochemical lead dioxide system, because it have a larger surface area, small grain size, and also these characteristics are interesting because they confer to the electrode a longer lifetime. After we decided to modify the structure of the electrode, changing the substrate, and we used a titanium mesh like this that was covered by an interlayer. This interlayer was made with a tin dioxide antimony dioxide coating that ensure the good adhesion of the lead dioxide that was electrochemical deposited, as I showed you before. And this new electrode was a good electrode for what concern the mechanical stability, and the requirements are good for the preparation of the system for the upscaling. All this optimization can be observed in an improved overall Faradic yield with electrode optimization. In fact, here I reported the first electrode I show you, with a Faradic yield of 85%, more or less. Modifying the electrode bath with the PVA, we have obtained an increase in Faradic yield, and modify also the support and stability of the system. We have obtained a higher Faraday yield. At the end, this type of material was suitable for the upscale that was realized by the other partner of the project. In summary, the electrochemical conversion was successfully performed on optimized lead dioxide electrode, reaching combined Faradic efficiency higher than 97%. This type of conversion is less energy demanding, or occurring at ambient pressure and temperature, and use a cheap catalyst material. The preparation procedure of the electrode is affordable, and the electrode is stable under reaction condition. And finally, we can conclude that this type of material is suitable for maleic acid production at industrial relevant condition. Thank you for your attention, and thanks also to all the work package 2 and all the partners for this activity. For question, you can ask in the chat.
Good afternoon, everyone. My name is Joost Helze. I'm from Vito, and I will shortly explain to you the part that Vito did in the Perform project, which was on the production of glucaric and adipic acid. So the initial project concept was, as already shown by Erwin, the transformation of glucose to glucaric acid and then onwards to adipic acid in a what's so-called paired tandem electrosynthesis. Paired in the sense that both oxidation and reduction reactions would carry on in the same stack or same electrolysis cell, and tandem cell in the sense that the product of the oxidation, the glucaric acid, would then be used for the reduction towards adipic acid. As it turns out, things have evolved a little different, and we, as Erwin already mentioned, noticed that especially the second step was very difficult to achieve. I would still like to elaborate further on the first part, and in the end of the presentation I will shortly reveal some of the new developments for the second part. But first, so the oxidation of glucose to glucaric acid. Glucaric acid is a diacid in a, let's say, currently in an underdeveloped but growing market. It's used for detergents, spreaders, food ingredients, but also more and more towards hydroxylated polymers. It's reached projected to have a global turnover of $1.5 billion in 2027, so that's quite substantial. And currently it's produced also from glucose, mostly with diluted nitric acid. But there's also some other production methods, for example, with gold, platinum, bimetallic catalysts with very high partial oxygen pressure, but even then the yields are quite disappointing. So in Perform, we would like to establish a route from glucose to glucaric acid and to study this also in an upscaled version using basically renewable energy and a renewable feed. So the glucose is not to come from a feed or food-based source, but actually from, for example, cellulosic biomass, which is then converted into glucose monomers. And of course, the whole idea of the electrocatalytic conversion is to use renewable energy to make the whole process more sustainable. Compared to an existing process, which also produces glucaric acid, but in a thermocatalytic way, the idea was to end up with a lower capex and opex of this electrocatalytic process, and of course energy and impact, and as well as the process intensification. So basically, glucose towards glucaric acid happens, it's a 6-electron transfer, happens in 2-3 stages, where glucose is converted to gluconic acid, which is a quite easy 2-electron transfer, and then to hyaluronic and glucaric acid, which is a bit more difficult, and you will also see this in the results later on, that this reaction goes a bit slower. There are some byproducts which are formed, like hydroxylated succinic acid, oxobutanoic acid, and oxalic acid. It requires strong alkaline conditions, and generally operations with diluted glucose will prevent humic-like products to be formed, but these conditions generally are not very suited for industrial applications. So for industrial applications, we want more concentrated feedstocks, basically. Of course, an important feature of the whole process should be the electrocatalyst stability. And as is known, diacids are very good complexing agents, so this could compromise this stability. So first of all, for the glucose to glucaric acid conversion electrocatalytically, we investigated several routes of direct electrooxidation using either gold or palladium or nickel iron catalyst, which were coated on 2 particles, mostly carbon nanotubes, where nanoparticles of either gold or palladium were coated on. But in fact, these tests, which were basically done in H cells, so very small scale, square millimeter size, basically, cells, these yielded only a few % of gluconic, and actually no glucaric acid was found. So then we shifted towards a mediated electrooxidation, which means that you use a mediator. And in this case, tempo was used as a mediator. This is the tempo molecule, as you can see it here. And with different mole percentages of tempo in a carbonate, at that time carbonate solution, we found substantial yields of gluconic acid and also glucaric acid. So this encouraged us to move this test further, and we try to screen it for longer periods of time. So actually what's happening, you can see here on the right. So this is the tempo molecule being oxidized at the electrode surface, and then oxidizing the glucose in the solution. Of course, with a mediated electrosynthesis, the main problem can become the recovery of the mediator from the electrolyte. So this is something to take care of, and this will be dealt with in the further slides. One thing also to, a possible strategy to circumvent this problem, let's say, is to immobilize tempo onto the electrode surface. And we try to do this with amino tempo, so which is basically an amino form of the tempo. You can see the amine form here. And we tried to graft it onto a carbon electrode, oxidized carbon electrode, and forming a amide bond with the electrode. And when we run some tests on it, we actually could see that there is some actually quite good conversion of glucose to gluconic, so the first stage of the oxidation of glucose, but we couldn't find any glucaric acid on this immobilized form of tempo. So then we shifted back to a mediated oxidation. In flow cells, we really tried to figure out what is the best type of electrode that we can use in combination with the tempo and the glucose. And we find out that in a micro flow cell, so this is only 10 square centimeter, we now moved from a few square millimeters in H cells to 10 square centimeter. We found out that a non-woven activated carbon fiber was one of the best electrodes to be used in combination with the tempo. When we did a longer-term experiment on this during chronoamperometry, so we operated the cell at fixed potential, we saw that we could achieve a Faradic efficiency towards glucaric acid of around 57.5%, almost 60%, and the same for the yield. So we could convert 60% of the glucose to glucaric acid, which was extremely nice at that time. So this was done during a 24-hour experiment. This then led to the following step, so the scaling up, which was one of the main goals in Perform, scaling up from 10 square centimeters in the microflow cells to 1,000 square centimeter. You can see the stack here. This is actually a single cell, which was designed by HYSYTECH. And where we started to run tests with the mediated glucose oxidation reaction. So we performed tests with 100 mole% of tempo at pHs around 11 to 12, and we followed the electrode degradation. So at a continuous feed of glucose, actually, this is not a batch experiment anymore. This is really a feed and bleed experiment where we use the big cell and continuously feed glucose. You can actually see quite nicely the evolution here of the glucose level, which is still fluctuating, but let's say fairly constant. And you can see that in the right graph, the increase of the reaction rate of the glucaric acid is still increasing. The blue line indicates reaction rate of the gluconic acid, the first step, which is decreasing when the glucaric acid is still increasing. Very nice. Of course, as I mentioned, also a DSP needs to be in place in order to remove the mediator from our electrolytes. And the first step that we investigated was electrodialysis, similar to line 1, where we could see that we could achieve a very good separation of glucose from the formed acids, both gluconic and glucaric acid. I will quickly go over this. Following then the final step of the downstream processing, the DSP, for the crystallization, we saw that we could actually selectively also precipitate potassium monoglucarate from the reaction electrolyte, so separate it selectively from glucose and gluconate. So it's a way to actually selectively separate the gluconate from the glucarate. This actually shows the effective separation, so the yields of gluconic and glucaric, when we added the anti-solvent precipitation. So the crystallization in this case was enhanced by adding an anti-solvent, and the anti-solvent here, which worked best, was methanol. So methanol actually proves also to be a very good way of either further refining the produced monoglucarate crystals. So this is what the total DSP scheme will look like, starting from the feed, which is glucose, tempo, and base, in this case potassium hydroxide, where we go to the electrocatalytic reactor, where glucose is oxidized to gluconic, which is GOA, and glucaric, GAA. And both are then separated in an electrodialysis unit where the glucose, tempo, and the base are recycled back to the reactor. So no loss there. And the gluconate and glucarate are still combined in the solution, and they're going to a crystallizer using the anti-solvent precipitation, where we are able, to separate the glucarate again from the gluconate. All this methanol, which is used in this cycle, can be recovered and recycled. So this is what it looks like in the lab. On the left, you will see the cell, so the HYSYTECH 1000 square centimeter cell, the internals in the middle, and then on the right is the electrodialysis cell that recovers basically the acids from the electrolyte. We also did a coupled test just to make sure that whatever we produce in the reactor also ends up in the right compartment. And as you can see here, the glucaric acid concentration is actually increased in the green one in the acid compartment of the electrodialysis, as well as the gluconic, but this is because there was no recycle of the gluconic acid. Okay, so conclusions for this part, line two, oxidation, is that tempo-mediated oxidation is possible at reasonable performance. We achieve a yield of 60% and 60% efficiency. We were able to upscale it to 1000 square centimeter, which is an industrial size reactor. And we have a very powerful separation with the electrodialysis for the separation of the acids from the electrolyte, and in combination with the two-step crystallization for robust separation of the acids, so gluconic and glucaric acid. 100% recycle of process streams was possible. Finally, I want to end with the second part. It will be very short. But it was already mentioned that especially the reduction from glucaric acid to adipic acid was quite difficult and not well achieved during the first part of the project. I will quickly skip this. These are all the experiments actually that have been done on the reduction of glucaric acid towards adipic acid, many experiments. Not very successful. In the end, also still some efforts being devoted to the, let's say, conversion of thermocatalytic catalyst towards electrocatalysts, and this could be a breakthrough. But we have found, taken a few steps back, and try to really scrutinize what is the actual mechanism that we are looking for. So from glucaric acid, we want to achieve, in the end, adipic acid. This goes over muconic acid, which is a molecule that you can see there with a double bond. And in order to prove this reaction or find the right catalyst in combination with the solvent, we then resorted to this model compound, basically, and tried several reactions, combinations of electrodes and solvents. And in the end, we were able to find at least one combination of electrocatalysts, electrodes, and solvent, which proved to be able to remove the double hydroxyl group, so the vicinal diol, to a double bond, as you can see here. So this is with one specific combination of electrodes and solvent. Of course, this needs to be further developed. We are now at the end of the project, but we will take this to the next level. We also try to protect this in terms of intellectual property. But there is still a lot of work to be done on the electrocatalytic synthesis of adipic acid, starting from glucose and from glucaric acid, basically. So I want to end the presentation with this. If you would have any questions, you can contact these persons, or of course directly via the Q&A in the chat, or through the coordinator to Erwin. Thank you.
Well, hello everybody, my name is Riccardo, I'm a scientist at TNO, and today I will tell you something about the work that we did on the pilot that you actually see on the background of this slide. So maybe a bit more about the, let's say, the focus, the motivation of this project. So what we want to achieve in this project is actually helping the electrification of the chemical industry. So actually going from bio-based feedstocks and renewable electricity and then generate something that can be actually used for the chemical industry. So, but how do we actually do this? How do we implement, how do we use electricity and bio-based feedstock to achieve this target? And here I would just want to take a bit of a step back and maybe mention concepts that already have been mentioned before in these presentations. So essentially, if you look back at what electrolysis is, you just take electricity, in this case a battery, you can run electricity through like electrodes and a solvent, in this case water, and you generate on one side hydrogen, which is your valuable product, but on the other side you generate oxygen, which is fairly useless, and you actually discharge that into the atmosphere. It has no economical value. So what we want to do in this project is to actually make use of both electrodes and generate two valuable materials at both sides of the electrochemical cell. And how do we do this? So we just need to envision, let's say, a different type of electrochemical cell, maybe a flow cell or something like that. On one side of the cell, we will do a reduction process. On the other side, we will do an oxidation. So we just need to, let's say, find a suitable starting material. We need to find target products, and we need to find catalysts that are able to do this sort of processes. Of course, most of this part was just mentioned, like finding catalysts was just mentioned in the talk before. And regarding, let's say, target products in this project, we choose maleic acid and valeric acid. And the reason for that is that if you look at maleic acid, it's a very nice molecule that is used quite a lot in industry for several different applications. But if you look at how industry is making this product, this molecule, well, it uses very harsh conditions, 500 degrees. You have a very sophisticated catalyst. 30–40% yield, and of course you produce CO and CO2 as a byproduct. So this is not sustainable. On the other side, we choose valeric acid, again quite a lot of let's say uses in the chemical industry. And again, if you look at how it is made right now, it's made with a homogeneous catalysis process that you actually need to recover your catalyst after the reaction, and again, high temperature and high pressures and precious metal catalyst. So this is something that we actually aimed to change and make it a bit more, let's say, sustainable, that we can actually help electrification of the chemical industry. So in the Perform project, one of the line, as already was mentioned, was going from, let's say, furfural to maleic acid on the oxidation side, and going from levulinic acid to valeric acid on the other side. Now, both, let's say, furfural and levulinic are bio-based. We use renewable electricity, so there is no fossil input in this process, and then we can actually also limit a bit of the CO2 emission, because we use indeed like non-fossil based materials and well, green electricity. On the other side, so by combining two different processes in one single cell is actually helping reducing the cost of production, because we're actually using the electrons 2 times to generate 2 different products and 2 valuable products that can be sold separately. Yeah, so as was already mentioned in this, a few times in this process, we actually moved from, let's say, a very low TRL level with very, very small reactors in the order of like a few square centimeters to begin with. Then towards the middle of the project, we actually reached 1,000 square centimeter electrode surface area with a very, very small balance of plant around, and from here we did a bit more of reactor and process development to actually, in collaboration with the partners, be able to build the actual power platform that is actually standing right now in our labs. Targets of the project for this pilot were 250 grams per hour productivity, and that's about 6 kilograms per day, with a very high Faraday efficiency. But very important in this project, we also looked at all the downstream processes. So we actually go from a crude electrolyte to pure compounds. And then we were also aiming to, let's say, demonstrate the reusability of the electrolyte. So after the downstream, just take the electrolyte and put it back in the upstream to generate more product. Yeah. So this is the pilot that we have now in the lab. As you can see, like on the right, you have the upstream with the electrochemical cell in the middle, and then on the other side you have the electrodialysis setup. That is the first step of the downstream process, and I will go back to that later. So when we started looking at this reaction, the first important thing that you need to understand is the reaction mechanism, because this is really relevant to actually later on make calculations or actually look at what is happening in your reactor. Of course, it's also this type of reactions typically are very dependent on the type of media that you have. So it's really different operating this oxidation in acidic environment or in alkaline environment. But as you can see here, if you are targeting maleic acid, then you better be off in acidic conditions. Even then, when you operate in acidic conditions, you see that the first step of the oxidation actually leads you to some sort of intermediates that actually evolve to one stable intermediate that is 5HFO. And together with that, you also generate formic acid at the same time. So this is really the reaction mechanism that we are looking at. So no matter what we do, we are going always from furfural to 5HFO. And then in a second stage, we can convert, in a second oxidation process, we can convert 5HFO to maleic. In this picture, we also see that we generate formic acid. Formic acid also has certain value. In this project specifically, we didn't really look at, let's say, recovering formic acid. But I will also maybe show you later that recovering formic acid is a bit unpractical because also formic acid can undergo an oxidation process, and then we are going to lose formic acid in our electrolyte. Yeah, so now I will just focus a bit on well, actually one single experiment that we did. So typical, let's say, conditions for our experiments. We have done, let's say, this sort of experiments more than once on, let's say, different conditions, but also different cell pairs. But typically, because we want to run this in a paired system, we have furfural on the anolyte side. We have levulinic acid on the other side. In this specific case, for furfural, we try to keep the concentration, let's say, low. So we start with 0.1 molar, and then we keep on dosing furfural throughout the reaction. Instead, for levulinic acid, we decided to actually put a 2 molar concentration and do no dosing. In this case, it was only like 2 cell pairs with 1,000 square centimeter per cell pair with a fumacep membrane, and we try to also keep the temperature constant, which is also a bit of a challenging part. So this is the type of, let's say, data that we get. So we can look at the, let's see if I can do this pointing. So we can look at the furfural concentration. So we see that we actually start from the 100 millimolar that we put in the reactor, but then like during the course of the first, let's say, 20 hours or something, we are not really able to keep the concentration constant. So the concentration goes quite high. However, after the first 20 hours, we have dosed in the needed furfural that we envision to use. And so afterwards, you see that the furfural goes down in concentration because we are consuming it. And eventually, after 100 hours of experiment, we consume all the furfural that we have in solution. Okay, so now if we look at the products, so now you see that with the blue line, the first thing that we make is 5HFO. And at the beginning of the reaction, we have no maleic acid production. So this is actually in agreement with the mechanism that we envisioned before, especially because we can also show that together with 5HFO, we also make formic acid. But let's say the puzzling thing is that formic acid is always difficult to recover, because you see that at some point the formic acid concentration goes down, and this is because you can oxidize formic acid to CO2. So you lose completely your formic acid in there. And this is also a problem because your Faraday efficiency is going to go down because you're using electrons to make something that is useless. But aside from this small issue, after a certain time, when we start to, let's say, build up a bit of concentration of 5HFO, and we start running lower in concentration of furfural, then at this point is where we actually start to making maleic acid directly from the conversion of 5HFO. Yeah, so this all looks very nice and very promising. We can look at the, let's say, the selectivity. This is also a reflection of what I just said now. At the beginning of the reaction, we only make 5HFO. Only when we run out of, let's say, furfural, we start to make maleic acid from 5HFO. If you look at the yield, in this case, we can combine the yield of, let's say, maleic acid and 5HFO. And well, here the yield is quite, let's say, decent. However, we need to realize that we have about 45% yield, but if you look here, we run out of furfural. So this means that we are losing quite a lot of furfural throughout our process. And well, I can comment on that a bit later. But the fact that we actually get 5HFO is not a big issue, because we know that 5HFO is an intermediate in our reaction, and we can feed it back to our reactor in a second stage after downstream processes. So we can keep on converting 5HFO later on. Yeah, so in this, just a bit of a summary here. Well, In this experiment, we actually obtained quite a lot of electrolyte that we are able to use in the second stage for downstream for purification. We have about 1.2 kilograms of produced maleic acid. So if we actually want to be a bit more careful in having a higher yield, we need to actually pay more attention at dosing furfural, keeping the temperature constant, and also like maybe choosing a bit better the membrane that we're using. As I said, we also looked at downstream processes, and as was mentioned before, from the upstream unit, if we look at the furfural to maleic side, the first step is electrodialysis to remove sulfuric acid. Then we have an nanofiltration step, and this serves as a concentration step to remove most of the water. And then we have a filter reactor in which we can do evaporation, crystallization, washing, filtration, all these sort of processes to actually get to maleic acid crystals. On the levulinic acid side, what we do a liquid-liquid extraction, and then we do a distillation. And then, for sake of time, I will only focus on electrodialysis. So this is the electrodialysis setup that we're using. We actually feed this maleic acid and sulfuric acid solution on this side, and what we are doing, we are shifting sulfates or hydrogen sulfates toward the concentrate side, and as a result, in the diluate side, we only are left with maleic acid and a tiny bit of sulfuric acid. We have actually run this process on a MOX solution just as a showcase, and we can see that we can reach a desalination, let's say, degree that is around the 80%, and within this desalinization, we actually remove most of the sulfuric acid, but we keep all the maleic acid in solution, so we lose very, very, very small amount of maleic acid. Next, we actually look at the real sample. So this is data from the real electrolyte that we got from the upstream unit, and again, in this case, we push desalinization a bit further to about 85%. But you can see that the maleic acid that we get is very constant. And also here you see that 5HFO stays in the same solution, but after crystallization of maleic acid, we can recycle 5HFO back to the upstream. In this case, because we actually pushed the desalinization a bit farther away than 70%, we also start to see, let's say, a loss of maleic acid in the concentrator. This is because we start deprotonating maleic acid and then also crosses the membrane. So next step, as I said, is nanofiltration. This we haven't done that yet with the real solution. We are busy at the moment, and then the next step is going to be the filter reactor to actually get the crystals. And with this, I would already like to conclude. So in this process, we actually show that we can work with let's say a stack reactor to make products at a relevant scale. We have demonstrated quite a lot of let's say technologies, and we are still busy through the end of the year to actually run the final steps of the downstream processes. And we also hope to actually demonstrate their reusability of the electrolytes. And with this, I would like to conclude and give the floor to the next speaker, Alex.
Okay, so good afternoon also from my side. My name is Alexandru Morosanu. I work for HYSYTECH as an R&D project manager. So bear with me, I'm paid to do this, so I have to present the company for those who doesn't know us yet. So HYSYTECH is a chemical engineering company that was founded in 2003. We are specialized in the design, development, and industrial implementation of new technologies and turnkey equipment. We are currently about 60 people working. We have also both the engineering team, the mechanical engineering team, and also the production facilities in Torino. We, a few years ago, 5 years ago, we also bought a Dutch company, still in cryogenics. That was an old Philips branch that was specialized in producing these cryocoolers that can reach very low temperatures, up to helium liquefaction, for example. And finally, last year we also have a new partner in the company that is Nippon Gases, that is basically part of the Mitsubishi Chemicals group. So it's a minority partner, but still now a partner of the company. Just two words about this. We have, let's say, the money is coming right now from biomethane plants, so we upgrade biogas to biomethane, so to natural gas grid quality. Then we have the bio-LNG plants, so the liquefactions that we, cryogenic liquefaction of natural gas that is done in collaboration with Stirling Cryogenics. And then the hydrogen production on site through highly integrated steam reforming technology. This is more interesting for the, let's say, R&D part, since we provide lab equipment, test rigs, prototypes for basically all kind of chemical, biological, electrochemical processes that you can think about. These are more, let's say, this. Okay, so these are more smaller scale, like at what we are looking in perform. At higher scale, these are TRL7, like 7, 8 equipment, and these are more, let's say, special industrial plants that we can provide as well. We are very active in many R&D projects. This is just the one that are currently running. The topics are very broad, from electrochemistry, biochemistry, bioelectrochemistry, thermochemistry, and photoelectrocatalysis, for example, just to name a few. Why do we participate so much in R&D projects? So it's basically to learn new technologies and try to intercept them in order to develop and bring them to the market, becoming basically a supplier of these technologies. You can see here a few examples. We start from very, let's say, lab scale equipment and upscale these technologies up to, let's say, demonstration plants at TRL7 and higher. But enough bragging about us. So moving to the Perform project, what we have done here, as you know by now, we have two electrochemical routes to synthesize different, let's say, monomers or chemicals that are used in the chemical industry. So here, basically, we had to develop a so-called PowerPlatform that had to let's say, perform these processes. So you can see, let's say, our main objective here was mainly in the technology, upscale and validation. So we had material development, design, and then we had to design and build the electrosynthesis pilot, the DSP units, and the process and do the process integration. And this is what we actually call the PowerPlatform. If we look at how electrochemical processes are scaled up, usually you have 3 steps. You start from the electrode materials. This is where you actually synthesize your materials in the lab, and then try to deposit them on different substrates, as you've seen from Rosalba's presentation, for example. Then you move to you move to the reactor scale up. So usually when you do the electrode material synthesis, you start with very small scale reactors like this and H cells, where you carry out your screening of the materials, and then you start moving towards, when you start to use the, let's say, the supported electrodes, you start to move towards flow cells, and you upscale from there the size. Then if you have to look also at the process size, so all the balance of plant that you have around your electrochemical stack. So this is an example. You start with small test benches. This is just an example of what we have done in the past for different processes, where you start with 100 square centimeter flow cells, and then you move to actual containerized units like this at, let's say, higher TRLs, where you can install them in industrial facilities to demonstrate their actual viability in industrially relevant environments. So I will be focusing mainly on this part. As mentioned, the reactor scale-up, usually you start with very small reactors. Typically, when you start with the materials screening, you use H cells, so in order to perform fast electrode material scaling, then you move to flow cells. Why do you move to flow cells? Because it's basically what you are going to do industrially. So industrially, in order to increase your throughput of your process, you need to move to a flow cell arrangement. Then this, let's say, is still at the lab scale, so up to, let's say, between 1 and 100 square centimeter, and then you move to more to bigger and bigger cells. In Perform, we had actually two stages of upscaling. We had the first stage that I call a big single cell. So we moved from the 10 square centimeter that Joost was mentioning to actually 1,000 square centimeter cell. This was a single cell that we provided to the partners for the initial testing. And then we had a second stage where we actually prepared a stack of these cells. So actually reaching with 10 cells the 1 square meter size of active area of the electrodes. If we take a closer look, so on this scale up, so the first in the single cell, we had, as mentioned, 1,000 square centimeter cell that has 2 chambers. The actual specification was to reach up to 200 milliamps per square centimeter in terms of current densities. This means that the cell should bear at least 200 amps. We had to design the cell in such a way that we can use different type and sizes of electrodes in order for the partners to develop them and to understand which is better for which application that we were testing. And then we had we have supplied to the 2 lines that were being developed, so the TNO and Vito, 2 identical cells to start testing the chemistry in them. So after a bit of back and forth between us and the partners, with receiving all the feedback about how to build the cell, which arrangement were better, and so on, we moved to the second stage of upscaling of the reactor, that is building a cell stack. For the cell stack, we build a bipolar arrangement stack, so that means that all the cells in the stack are electrically connected in series. With 10 cells, we actually reached the 1 square meter cell electrode active area. Furthermore, also this stack can be, let's say, it's modular. You can replace the electrodes relatively easily, and also you can work with a different number of cells in the stack, so starting from 1 to 10 cells. If we look at the process scale up here, we have gathered all the process specifications from our partners about which are the chemicals that we can find, and we've gathered all the information needed to develop the process. So we've done all the detailed engineering part from material, mass and energy balance up to, let's say, mechanical design, electrical design, and so on. One important aspect of the development was, of course, the safety of the system. That we've analyzed and discussed with the partners during the development, and finally we performed the procurement and construction of all the pilot. You can see here this is the 3D model of the upstream system. So on the left you can see the 1 square meter stack that goes in the middle of the setup. Basically, the setup has 2 loops, one for the catholyte and one for the anolyte, with all the equipment and sensors needed to control the process. We have also an HMI system that the operators can interact directly with the system, and all the safety equipment around it. The same was done also for the AD. We had also in the scope the supply and the development and supply of the electrodialysis unit. This has also been designed for both ED processes to be carried out, the one for line 1 and the one for line 2. They were slightly different from each other. One required 3 loops, the other 4 loops, because of how the process worked. So you can see the stack here, the electrodialysis stack for line 1, and all the equipment that is needed actually in the setup to run it, and so on. Main challenges that we had to face, one was the material compatibility. So the electrolyte solution is quite corrosive to metals, and also the 2 lines work, one in acidic, one in the other in basic media. It was difficult to identify the correct materials, but it required some tests from us to be performed. The setup needed to be highly flexible, so both processes needed to be carried out in one equipment. We had to have high rangeability of all the equipment in the setup, as I was mentioning. For the upstream, you can run it with 1 cell or 10 cells, so it requires the equipment to be able to do that. A fully automatic system, and we were working with high voltage equipment as we were going to big stacks. And also we had to be sure about all the safety aspects. So we were producing hydrogen and oxygen as byproducts from our system, and also we were working with some toxic substances. So if we have to look at future perspectives here for upscaling, we are currently in the so-called TRL Valley of Death. So what does it mean? That's basically we are in a place where most of the projects and the idea, let's say, die because of lack of of investment, for example, or uncertain viability due to, let's say, not so much demonstrated in scalability in real-world application. So what we have to do now is to do some funding scouting to proceed with our, let's say, endeavor in electrifying the chemical industry, and especially on our processes to try to bring them closer to the market. and to have, let's say, improve our, to start our industrial adoption of these processes. Yeah, and I think this is more or less all from my side.
Now we will see the 3 videos. First, the final video with Erwin's comments, then the TNO, and then Vito's.
The Perform project started more than 4 years ago now, with the ambition to realize a TRL 5.6 pilot installation for the conversion of biomass-based feedstocks to chemical building blocks for the industry. I think it was quite a rush. The project will end this year. If I look back now, we started with the development of the feedstocks, with the electrodes, with electrode materials, and then we went into the lab and we tried to scale up to lab scale the reactions, which was quite successful. And then together with HYSYTECH we designed and built the pilot plant with the partners in the consortium. It was a pity that Corona came in between, so for a couple of years we could not meet up. We had problems with realizing the pilot, material was scarce, lead times of components was very long, people could not work in the lab, labs were actually closed, and we still kind of improvised and recovered from that by having Teams meetings. And I'm especially thankful to my project officer of the European Union that they allowed us to extend the project with almost a year, and we were allowed to really reach the objectives of the projects this year. So I'm happy with that. But it was a rush, a great time, challenges overcome, and I'm looking forward to the next project in this area. So we're here in Delft at the laboratories of TNO, where we have realized the Perform pilot installation. And we just went to the lab, we went back up here, and I think everyone was quite impressed, and right so, because we have done a lot in the last years, realized the upstream electrochemical pilot, we designed all the processes around it, we realized all the DSP, so the downstream processing equipment, which is quite an accomplishment in those years. I think also the other partners in the consortium did a great job in that, developing the electrocatalysis, the electrodes, especially also HYSYTECH, of course, realizing the design and the realization of the pilot plant. So if you ask about accomplishments, I think we did well. However, also, of course, there's also the however, because it's still a research and development project. We're currently running the pilot. It's running for just a couple of weeks now, and we have some nice results, especially on the line 1 research, where we convert furfural to maleic acid. And we have quite some production also there already, which is within the targets of the project. However, for the other line, we couldn't do all the piloting. This is done on a smaller scale by Vito in Belgium, which was explained in the other video. But I think we had quite some milestones. We didn't finish the project yet. We have a couple of months left. We would need industrial interest of a company or a consortium of companies that are interested in investing this kind of technology to really make the chemical industry more sustainable. So whether from bio-based materials, whether from CO2 or from other carbon feedstocks, we have to make our chemistry, our industry circular. And then, of course, we also have to develop all the technologies that use sustainable electricity, sustainable energy. And there's still a long way to go. So I hope that we can, after the Perform project, have a couple of new projects developing this technology further. What will the future bring after the project? I believe that there's still a long way to go. We are now at TRL 5-6, quite successful with the pilot, but for the future we still need to scale this up further. And for that we need support of the industry, of investors, to go to a big pilot of TRL 7. And we're looking forward to cooperate with companies that would want to develop this technology further with us, whether with the routes that we have in Perform, like the maleic acid or the glucaric acid, whether another route with another molecule that's interesting for the industry.
We are here today in front of the Perform Power Platform that we developed with our partner HYSYTECH. This is the electrochemical cell. This is a unique cell, 1 square meter surface area, where we convert bio-based feedstocks into molecules that are relevant for the chemical industry.
Welcome in Delft at TNO, at the laboratories of the Sustainable Process and Energy Systems Department, where we realized the Perform pilot. We just had a successful workshop and we had a lab tour where everyone could see the milestones that we accomplished in the lab. Especially the electrochemical pilot is very impressive and we had some nice results already with it. But also we showed everyone the DSP, the downstream processing equipment that we realized and that we're currently using in the lab to do the demonstration of the project, and we hope to finalize all this work towards the end of the year.
Within the project, we not only developed the electrochemistry, so the electrochemical transformations, but we also developed all the downstream processes that are needed to go from crude reaction mixture to pure compounds. For example, if we focus on the maleic acid line, the first step is electrodialysis. This is again electro-driven separation technique where we use renewable electricity to remove sulfuric acid electrolyte from maleic acid. The next step in the downstream process is a further concentration of maleic acid, and we do this with nanofiltration. After the nanofiltration, we use a crystallizer reactor where we go from a liquid solution of maleic acid to crystals of the pure compound. When looking at a valeric acid side, the first process that we do is a liquid-liquid extraction using an additional solvent. And after that we do a distillation where we get the valeric acid up to 99% pure. We not only produce one relevant molecule, but we produce two relevant molecules at the same time within the same electrochemical cell, within the same infrastructure. This allows us to increase efficiency by 50%, and without being bonded to fossil-based stocks, we can also reduce CO2 emissions by, again, about 50%.
The main objective of Perform would be to provide a sustainable alternative to certain chemical processes, to chemical industry in general. One way we can do this is by using a different feedstock. In the case of Perform, we switch to a bio-based feedstock. So we take away the fossil-based feedstock in classical or conventional chemical industry and we replace it by a bio-based feedstock. And on the other hand, we're also focusing on electrification. So electrifying the process, converting the bio-based feedstock in an electrochemical process to the desired components. Vito's role in this project is mainly on the development and demonstration of one specific reaction. And this reaction is the conversion of glucose to glucaric acid and finally to adipic acid. Adipic acid is a compound which is readily used in chemical industry and mainly in polymer industry for the synthesis of nylon 6,6, a very common polymer. And what Vito actually focuses on is first the oxidation of glucose to glucaric acid, and in the subsequent step we will develop also the reduction of glucaric acid to adipic acid, the desired component basically. So we will develop the reaction, the electrochemical reaction in this process, but we will also focus on the DSP, the downstream processing so-called, which is the separation and the purification of the component that we form. Gluconic acid and glucaric acid are formed in our reactor and are separated by a process called electrodialysis. Electrodialysis actually selectively takes out glucaric acid and gluconic acid from our reaction mixture, and that's what we further will use for the separation and for the purification. This concentrate of gluconic and glucaric acid will then be transformed to a cooling crystallizer, and there we will drop the temperature, limiting the solubility of the glucaric acid and therefore creating also precipitates and pure glucaric acid crystals. To further increase the separation efficiency, we add another anti-solvent, we call it. Actually, it's a solvent that is used to lower the solubility of the glucaric acid in this mixture, which further increases the productivity of this separation. All these crystals can then be collected from the different process steps, and they can be further purified by using this anti-solvent to wash them. And all the washing water, all the washing liquid basically, which contains water but also the anti-solvent, can be recovered by distillation in a subsequent step. So the main benefits of the Perform process are twofold. On the one hand, we use a carbon neutral feedstock, glucose, for example, derived from cellulose. And on the other hand, we can plug in our process into the renewable energy grids. So organic electrochemistry is still quite young. During the past 5 years, very promising results have been shown in literature as well. Upscaling is quite new and still many hurdles need to be taken, but the prospects of developing a sustainable and carbon neutral process to the existing fossil-based route is very rewarding and should be really explored further.
And it's very important for industry and for academic world is how to convert selectively glucose to glucaric acid. And it's a very challenging project.
Thank you. So now we will go with the questions and answers part. There is one in the live chat, and I think, Erwin, maybe you can answer this. What is the biggest challenge to take this technology to the market?
So the question is, what is the biggest challenge to take this technology to the market? The biggest? Well, there are several challenges. There are technical challenges and there are commercial challenges. I think the biggest technical challenge is that we are still at a relatively low TRL, 5.6, and there are still a couple of hurdles to be taken to take it to a pilot plant on TRL 7 that would really work for thousands of hours reliably. We are not there yet in this project. I would like to have another year with a year funding, and then we could really go there, but at the moment we run out of time and out of budget. So that's a technical challenge. On the other hand, you have the challenge on the economy of the process. Of course, it's based on bio-based feedstock with a certain price. It's also based on renewable energy with a price. And both have a large impact on the cost of the product. And at the moment, it cannot compete still with fossil-based products. So the big challenge is that there should come regulation, for example, green premium in the market. There should come some legislation to make it possible that companies can really earn money with producing sustainable chemicals. Because at the moment that is not really possible, not in the EU, not in the world. It's a world market, and the chemical industry cannot afford to invest billions in new technology to produce on the same market where other producers from China or Asia, whatever, would produce from fossil fuels. That's simply not possible. So that is the biggest challenge with respect to the market. So we need politicians for that. Is that a good answer? Yeah. I don't see anyone online, so I really don't know, but yeah.
Anyone else have a comment to any of the speakers for our final event?
Give me another question. Any question.
You think I should ask the question? Yeah, I should ask the question. I think...
Could you state your name? And
I'm Oleg Perlic. I'm from a company called Perstorp. We produce a lot of molecules, organic molecules, ending up in tens of thousands of different materials and products. And that is very challenging to change. And first feeling is what you do is to just replace a oil-based raw material to non-oil-based raw materials, one-to-one, not to change the technology, because that is what you do. What is your opinion or why we should go to change technology from thermo-based technology, and you just change a type of energy instead of oil warming up, you use electricity. Why to go to the really challenging electro synthesis, you can say?
Why to go there? Well, that was on the basis of this project. Still a question. Well, I agree that at the moment where we are now, you could not definitely say that you want to go completely electrochemical. It depends on the process, on the molecule. It depends on the capex, on the opex. On the other hand, the benefits could indeed be that you have less waste, that you use less energy, because energy getting more scarce in the future because of the conditions, the reaction conditions. But if you say, yeah, we have already a thermocatalytic process, it already works well, and it is in competition with a new electrochemical process, yeah, then of course the designers of the electrochemical process should prove with a techno-economic analysis and a business case analysis that really you can compete with a thermocatalytic process, and you should even be better than that, of course. Otherwise, you would not scale up. But I have the feeling that we are not there yet, and I have the feeling that if you're using direct catalytic conversion, there are certain advantages that were presented today by different speakers, that for certain reactions and molecules could certainly be more beneficial than the current thermocatalytic conversions. I'm not claiming to have the real answer, but I'm saying that, yeah, we need to find out with a proper techno-economic analysis which is the best in what case. And that we actually did not fully do yet. But if you say, I already have a process, I can already do furfural conversion to maleic, thermocatalytic, and it is energy-wise better, or capex-wise better, or maybe the location, or maybe you have heat available and not electricity. It depends on all these factors in the future and the cost of the energy, what kind of route you will implement. I mean, there is a lot of technology development at the moment for sustainability, a lot of routes based on a lot of feedstocks. You can go from CO2 to anything. You can make hydrogen first, then you can do hydrogenation, you can do all kinds of processes. But I've seen a lot of comparisons and a lot of articles, analysis compare different routes, but there is no definitive answer yet. I'm also looking for this answer. What is better? Shall we go left? Shall we go right? Companies come to TNO, they ask us, should I go left, should I go right? Well, we can make a comparison, but you have to make the business case yourself in your company, your location of your production site, what would be best for you. In the end, there is no yes or no yet. So all what we can do as researchers, as research institute, as university, is try to develop the most interesting routes as far as possible, such that we can decide, yes, we can go on or we stop this. I think that is the best answer I can give you now. Okay.
No one has another question. Maybe I will ask you to stand here and maybe we can take a group picture.
All
and
right.
After that, we can go to the other room for our aperitivo. And
Then thank you everyone, also
Thank
online. I guess then
Yes.
we close
To
the
the
online
camera.
session. We closed the online session.
yes,
Yeah.
we're still on, yeah.
Oh, we're still on. It's on. Okay. Yep.
Thank you all.